Right, hello students. Today we will learn constraint optimization, linear programming, okay? And you will observe that we have already gone through these contents in the past before the first sessional, so you will definitely now enjoy solving the problems. Okay, so constraint optimization, of course we are talking about the constraints as well, and we are talking about the objective function. Okay, so the basic linear programming problem consists of two major parts. Now please remember this point, very important point. What are the two important ingredients? Objective function and the constraints. Okay, now the target is that we want to find the max. Let us say that Z is the objective function and we want to find the maximum, or we want to maximize it. Okay, and what is Cj? Cj, we can see these are the coefficients, but we call them payoff of each unit of the jth activity that is undertaken, right? And what is Xj? Xj is the magnitude of the jth activity. Thus, the value of the objective function is the total payoff due to the total number of activities n. And you can understand the meaning of this payoff with the help of a practical example that we will go through during this lecture. Okay. Now, the constraints can be represented generally as an inequality. You can see this inequality here. Okay. And some constants and some variables, where Aij amount of the jth resource that is consumed for each unit of jth activity, and Bj is the ith, Bi is the ith resource that is available. Okay, so that is the resources are limited. The second general type of constraint specifies that all activities must have a positive value, right? So we need to remember this point. The second general type of constraint specifies that all activities must have a positive value. Usually when we talk about, for example, a material, we can say that its quantity is positive only, right? So that's why we can consider this inequality as a constraint. Okay, you can utilize this information in the form of a constraint. Okay, now this is a problem. Now students, today we will solve this problem using two different methods. So let us first understand the problem statement. The following problem is developed from the area of chemical or petroleum engineering. However, it is relevant to all areas of engineering that deals with with producing products with limited resources. The point is limited resources. Okay, so that's why we want to optimize the situation. Okay, so suppose that a gas processing plant receives a fixed amount of raw gas each week. Okay, raw gas. Okay, and then the production, regular, premium, and the resource availability. Okay, so we have made a table here. All right. So the raw gas is processed into two grades of heating gas, regular and premium quality. These grades of gas are in high demand. That is, they are guaranteed to sell and yield different profits to the company. However, their production involves both time and on-site storage constraints. So now we are talking about the constraints. Which constraints are we going to consider? For example, only one of the grades can be produced at a time, and the facility is open only for 80 hours per week. Okay, so production time, total production time is 80 hours per week, for example. Okay, further, there is limited on-site storage for each of the products. All these factors are listed below. Note that a metric ton or ton is equal to 1000 kilograms, right? So this is the input data, okay, which is given to you. Okay, they are talking about the raw gas, the production time, and the storage. Okay, 9 tons and 6 tons for the regular, 9 tons for premium, 6 tons. Okay, and here we have also made a row for the profit. Okay, for the regular we are expecting 150 per ton, and for the premium we are expecting 175 per ton. This is the profit, right? Now we want to now what is going to happen now, students? Now the plan is that data is given to you. You will optimize the situation. You will make an objective function, and you will make the equations for the constraints. This is the plan. Okay, now let us learn how we do that. The engineer operating this plant must decide how much of gas to produce to maximize profits. If the amount of regular and premium produced weekly are designated as X1 and X2 respectively, the total weekly profit can be calculated as total profit is equal to, what is happening here? The total profit is equal to 150 times the regular and 175 times the premium. So 150 X1 plus 175 X2. Okay, so this is the objective function. Okay, so you can see how swiftly we have designed the objective function. Next, the constraints can be developed in a similar fashion. For example, the total raw gas can be computed as total gas is equal to 7x1 plus 11x2. Here you can see that 7x1 plus 11x2. But for the constraints, we usually consider the inequalities. So we will say this total cannot exceed the available supply of 77 meter cube per week, so that the constraint can be represented as this inequality. Okay, now I have got one constraint, and now how many variables are there? Two. Okay, so I would like to have some more constraints so that I can get a clear picture in my mind. The remaining constraints can be developed in a similar fashion with the resulting total formulation given by this is called LP, stands for linear programming. Okay, so maximize Z is equal to 150 X1 plus 175 X2. Okay, maximize the profit. This is the objective, and these are the constraints. Now, number one for the material, number two for the time. Now, this one is for the regular storage, and the other one is for the premium storage. And then you can see here that positivity of the constraints. X1 is positive, X2 is positive. Okay, now today's task was to learn how to develop a optimization problem, linear programming. Okay, and tomorrow we will learn the graphical solution of this model. And for your personal convenience, before the video, you can read the book, page number 389 and page number 390. And of course, please open MATLAB as well and try to sketch these lines on the same graph. You will see that you can easily obtain these regions. So tomorrow's task is we will discuss figure 15.1. What is happening in figure 15.1? We have sketched all the objective function and all the corresponding constraints on the same graph, and now we are talking about the maximum. Okay, so in the next video we will discuss this picture. Okay, so hope to see you. Thank you so much.